All right, how's everybody doing? Welcome back to our Math for Healthcare video series. We continue on in our quest for looking at probability distributions. And in order to do that, our next bit of counting techniques, we need permutations and combinations. So let's see how they're going to help us. First, recall, this is kind of something that we should be able to do from last time. A baseball team has 9 players. How many ways can their batting order be arranged? All right, so go ahead, hit pause, and figure that out. You should be able to answer that. Turns out it's 9 factorial, right? It's just the same as saying how many ways can I arrange 9 distinct books on a shelf. We assume the players are distinct. We don't have any clones or anything going on, right? All right, so 9 factorial. Turns out that's about 360,000, 363,000-ish. But that's how we did that. We did 9 factorial, right? And here the order matters. And remember that factorial symbol, right? Let me just remind us, what does factorial mean? 9 times 8 times 7 times 6, all the way down to times 2 times 1. Revisit the slides from last time if you don't remember that. They should be right there for you. Okay. So now, suppose 8 people are running for office. How many ways are there to rank your top 3 choices? Okay, so again, we got 8 distinct items, and we're arranging 3. Okay, so how do we do this here? Well, certainly we could use our multiplication principle. So it's 8 times 7 times 6, right? Now, just like with factorial, we have notation for this. We call it permutations of 8 things taken 3 at a time. Right? And you'll see that printed out in all its detail on the next slide. 8 things, say it just comes from the formula. It's very much like a factorial, except for it doesn't go all the way down to 1. You stop somewhere. All right? And just so you see, note is in Desmos, you could write this as NPR. Okay, so the permutation of 8 things taken 3 at a time. And so we see it here. We have, simply write this. It's much easier than a graphing calculator to do. And that's the permutation of 8 things taken 3 at a time. And so that looks like it's 336. Now, here's the full-blown list of it, and our notation here. So for permutations of n distinct items taken r at a time, here's our formula. It comes from the multiplication principle. However, and both work, but use Desmos, please. Use Desmos in this in order to find out what our values are. You don't need to be doing this by hand, especially when the numbers get large. I guess one last note is that this only holds when r is less than or equal to n, which makes sense because if, say, you had 10 things, you can't reach in and grab 11 out of there, right? Okay, so suppose 100 people are running for office. How many ways do they rank your top 20 candidates? Right, so here, this is the permutation of 100 distinct items taken 20 at a time, right? If you're doing the multiplication principle, you have 20 dashes, and it's going to be 100 for the first, 99 for the second. But we don't want to be writing all that down, right? No, we simply go and we say, oh, okay, so I want the permutations of 100 distinct items taken 20 at a time. All right, and so that's quite big, 1.3 times 10 to the 39th. What did I say? 1.3 times 10 to the 39th. Huge number. Huge number is going to come up. This is why we learn scientific notation. All right? Now, 5 names are written on a slip of paper and put in a hat. 3 names are drawn and written down in order. How many ways are there to do this? Okay, well, so in order, what? This is permutations of 5 things taken 3 at a time. And we could plug that in Desmos. I'll let you do that on your own. You don't need to see me do it. But since we know the formula, let's say that's permutations of 5 things taken 3 at a time. It turns out that's 5 times 4 times 3. I guess. It's going to be 60, right? 60. And notice that, remember, this is the same thing as, okay, I got 5 people, I want to rank 3 of them. How many ways is there to do it? There's 60. Also, like our previous lectures was, I have 5 books. I want to arrange 3 of them on the shelf, right? Remember, arrangements is orderings of things. That's what we mean by permutations in mathematics, orderings, okay? Now, on the other hand, what if we don't care about the order and the name, that the names come out of the hat in this case, okay? So we're selecting a committee of 3 people, a committee here, because order doesn't matter. Then it doesn't matter which order they're in, just who's in the committee. Well, much like how we did the permutations with non-distinct items, like how many ways to arrange the letters of the word mama, well, we just got to divide out by all the orderings of the things that we don't choose. In this case, all the orderings of the 3 things that we do choose, right? So here we got to divide by 3 factorial, because that's how many ways to arrange 3 distinct items. And these are the people on the committee. But instead of being first, second, or third, it doesn't matter. You know, Bob could be, in the previous one, let's say Bob was first, Jill was second, and Cindy was third. Well, a different thing in that one would be Bob's second, right? But that's not the case here. This would be they're all the same. So here we want to divide by that 3 factorial, and we end up with 10 ways. 60 because 3 factorial is 6. Remember, there was 60 permutations of 5 things taken 3 at a time, and so we have 10 ways to choose a committee of 3 people from 5 candidates. In general, we call this a combination. All right, that's our other thing. This is where order doesn't matter. So it's a combination is a subset. Remember, subsets don't have any order of R elements of an n element set without regard to order. The difference between permutations and combinations is that with permutations, order matters, and combinations, it does not. All right? I like to think of combinations as I got a bag of things, items, distinct items. I'm reaching my hand in there, and I'm pulling out R of them. How many ways can I do that? The way we notate this is n choose R, whichever way you write it is okay. And I should note that for Desmos, they put n, capital C, R, and then 10, 3, comma 3 for 10 choose 3, right? Now, notice this really should say for this 10 choose 3, I mean, like I'm giving you a specific one. So we're going to use our calculators for this too. I do give you the formula in general, a number of combinations here. This n choose R, it's, well, this formula, I'm not going to read it out for you. You could study it and think about it. We basically got to it by using this here. But we are going to use Desmos. I want you to use Desmos to calculate these. You really shouldn't use using these formulas. Now, a couple things that come out of these formulas, and just by thinking about it, that I do think is worth writing it down, is n choose 0 equals n choose n. All right? If there's n things in my bag, I'm choosing out 0. Well, there's only one way to do that. It's the empty combination. If there's n things in my bag, there's only one way to do it. I got to pull out all n of them. And so this is 1. And choose 1 equals n choose n minus 1. Right, what? Right? If I'm reaching in a bag with n things and I'm pulling out one at a time, how many ways that I could do it? There's n ways. There's just the n different things. All right, and these equals n. These are really helpful to memorize or have written down while you're doing your homework. It just saves some typing on, of course, type them all on Desmos, but sometimes it saves the typing there. And I guess one fact I'd like to state, it's a little less necessary to have with you all the time, but choosing R things is this from n is the same as choosing n minus R things from n. Why is that? If I have a bag of n things, I'm pulling out R, I'm leaving n minus R of them. So it's one or the other, right? You're going to get the same number of things. Okay, so let's try and use this in practice. How many ways is there to select a committee of 3 senators? If you're unsure, there's 100 senators total. All right, so in this case, notice committee. Order doesn't matter, so I'm going to use my choose function, 100 choose 3. Yeah, I'm just going to, so you could see me plug this in, I guess. Very similar to permutations. C, oops, sorry, N. I'm taking, I want to know what 100 choose 3 is. Turns out that's about 162,000. Right? What I said is 161,700. That's how many committees of 3 senators from 100 there is. And just remember, with all these, we're saying with disregard to any bias that we have, this is randomly choosing. I actually like this one for choosing it because I picture all 100 senators in a bag, and I could reach in that bag and I pick out the 3. How many ways can I do that, right? Okay, so now currently there's 25 female senators. What is the probability that a committee of 5 senators has 1 woman and 4 men? All right, so now we're asking for a probability. It's really not any different than what we've been doing, okay? We just got to put in some new counting techniques. Let's see what I'm saying. First of all, note that here we have 5 senators and not the 3 originally, right? So what is the probability that a committee of 5 senators has 1 woman and 4 men? Well, and remember, probability problems, we want equally likely outcomes in our sample space, finite. And we use, don't forget, what do we use? The probability of an event E equals the size of E over the size of S when we have a finite and uniform sample space, right? So here, let's just say E is 1 woman, 4 men when choosing 5 senators, right? Now, first thing we want to do is, just like in last section, what do we want to do? We want to find the size of our sample space first. Notice, we don't want to list out all these. We just want to find the size of it. No, right? For probability, all we need is the size. Okay, so so what do we got? What's the size of our sample space here? What are we doing? It's 100 choose 5. Right? Just so you know what this equals. That turns out to be equal to 75,287,520. Okay, you could go ahead and plug that in so you can see the number better written than the one I have there. But somewhere about 75 million. Okay, that's the size of our sample space. You definitely don't want to list all that out. Now, how do we find the size of E? Let's think about this. Now, we want to force that we're choosing one woman. So in general, with these types of problems, I tend to think of, when I'm finding the size of the sample space, I think of all the women and men, or whatever the different kinds of people or objects are, all the women and men, all together. I got this bin of 100, and I'm choosing out 5 of them. That's all, they're all together, men and women in one bin. Then, for the size of our event, now I separate them into 2 bins. I got the bin with just women and the bin with just men. And I'm going to pick in the, how many ways can I pick the woman? And how many ways can I pick the man? So notice this is using our multiplication principle with the combinations that is possible. Well, how many ways can I pick the woman? Well, there is 25 women, and I'm choosing 1, right? From our last slide, hopefully you remember that's 25. How many ways can I pick? So I really should pick the 4 men. We could do it all at once, right? That's going to be, and we want to do it all at once. We don't want to go through 4 different men and multiply them, because then we'd have ordering there, right? So now we have how many? 75 men, and we're choosing 4 of them. And I multiply those 2 together, okay? So in the end, we get the probability of choosing 1 woman and 4 men when choosing a committee of 5 senators is 25 times, actually I'm going to write this as 25 choose 1 times 75 choose 4, right? Divided by, right, the size of our sample space, 100 choose 5. Now here, I'm going to show you how I would do this in Desmos. Yeah, I have 100 choose 5 already, but I would really do this all together. So we want to do, now so here, instead of 25 choose 1, I'm going to put in just 25, because we saw that, right? That's my little shortcut. You need to, you could put in 25 choose 1. And then I want to choose, what do we got? 75 choose 4, that's the number of ways to choose the men. 25 ways to choose the 1 woman, and for each of those, there's 75 choose 4 ways to choose the men. And then I'm dividing by the number of ways to choose a committee of 5 from 100. And there we go, we get our probability of about 0.4, or a 40% chance that we end up with 1 woman and 4 men. That's exactly 1 woman and 4 men, okay? Now let's go back to our slides here. Now, what is the probability that the committee of 5 senators has at most 1 woman? At most. So let's see. One way we could do this, that's, notice that you can't have a woman, 1 woman in the committee of 5, and 2 women in the committee of 5 at the same time, right? So they are mutually exclusive, and we're going to take advantage of that, right? We'll say, want the probability of at most 1 woman. Well, that's the probability of 0 women plus the probability of 1 woman. All right? 0 and 1, those are 2 different events, and they're mutually exclusive. And it's that or. Remember the addition we think of, that's when we're using the word or. It's not and, it's or. Okay? And just recall, we don't have to worry about subtracting out the intersection. Why? Because they are mutually exclusive. All right, so when we do that, we know that that's going to be about, well, I already got the first one, right? We did that. One woman was 0.4. Well, maybe I'll write it in order. Sorry about that. So let's see, 0 woman, that's going to be, well, maybe I'm just going to write this as one fraction because they're really both over. They both have the same denominator, right? 100, choose 5. And on the top, we got 0 women. It's going to be 25, choose 0, times 75, choose 5. And then probably 1 woman is going to be 25, choose 1, times 75, choose 4. Now remember that numerator is the number of ways. The denominator is your size of your sample space. Again, it's a number. All right, this order is kind of in my way now. Let's go. How would I calculate that? Let's go to Desmos. That's going to be, I'm going to just use this one. Oh, I want that in there. Just use parentheses here. Plus, now what's 25 choose 0? Remember, it's just 1, so here we just have to do the 75 choose 5, all men, right? That's what that thing. Okay, and so we end up with 0.63 or 63% chance, right? This is 0.63-ish. Now, why may this be useful? Well, what we're going to move towards and we're going to want to start thinking about is this is the probability if we just chose at random, right? So now someone may be wondering, let's say we got a committee with 1 woman on it. You know, it's possible someone says, well, wait, was the people making the selection, were they biased and choosing men instead of women? And this probability tells us probably not, because it was highly likely under randomness, not looking at gender, there's 63% chance that you get 0 or 1 woman, or at most 1 woman. Right? And this is in general how we want to use this randomness idea, measuring against what's happening to get an idea how unlikely or likely it would be in randomness. Right? All right, let's see here. In a conference of 9 schools, how many interconference football games are played during the seasons? Teams could all play each other exactly once. All right, you may take a minute, hit pause, try and work on this. Turns out that we have 9 teams, and we're choosing 2, right? How many different ways are there to do that? There's 9, choose 2. By the way, this turns out to be, 9 times 8 divided by 2. Right? Don't worry about the formula again, just letting you know. And because why? Because some people, they make a mistake and do 9 times 8, right? And I just want to show you the difference. You need to take the order out of it because they're only playing once. 9 times 8 is a permutation of 9 things taken 2 at a time. And that would be if they play each other each twice and there's a home and an away game. Then there would be 9 times 8, right? But in this case, how many times play each team once. 9 choose to. So yeah. Now, let's see. A space shuttle crew consists of a shuttle commander, a pilot, and 3 engineers. The shuttle commander and pilot are to be chosen from 8 candidates, and 3 engineers are chosen from 12. How many such space shuttle crews can be formed? All right, so we want to use what we've learned in combination with the multiplication principle. See, that doesn't go away. You're still going to need to use it sometime. We saw it on the last problem we were counting men and women. We used the multiplication principle. All right, so here we got to do what? The shuttle commander. We got to do the pilot, and then the engineers. All right, so let's see. How many ways is there to choose the shuttle commander? Yeah. Well, there's 8, and then there's 7 ways to choose the pilot after that, right? And those are different positions, right? When Bob is the shuttle commander and Alice is the pilot, that's different than when Alice is the shuttle commander and Bob is the pilot. Now the engineers, we don't have any kind of gradation on them, right? There's no difference between engineer 1 and engineer 2 in this case. So what are we doing? We are choosing, what do we need here? Three engineers from 12. And so how many such space shuttle crews can be formed? 8 times 7 times 12, choose 3. Okay. And just note this is really permutations of 8 things taken 2 at a time times 12, choose 3. You don't have to think about it that way, but I do got to show you. And now I'll just put this in calculations. And we okay. And so that comes out to be 12,320 different ways. And notice we paid attention, so this is asking for ways, not a probability. What is the probability of 4 heads when tossing 2 coins? Okay. Let's see. What do we got? What's the size of our sample space, right? That's how we want to start. We're tossing 10 coins. We saw this in the first video. We used the multiplication principle to get this is 2 to the 10th. If you don't remember that, go ahead and look back in that video. All right. Now, that's our denominator, right? How about now? How many ways are there to get 4 heads? This is a tricky one. Because what we have here, first coin, second coin, third coin, fourth coin, 10th coin, right? First, second, third, fourth, and 10th. And we think of them in order, okay? So what can happen here? Well, one possibility, right? And this is good when you're doing counting problems. Write down what a possibility looks like, yeah? So in this case, what do I mean? Well, I could get heads on the first 4 tosses and tails on the last 6. That's 1. Right? So we have at least 1 in our numerator. Right? We're counting our event E of finding probability of 4 heads. Okay? What else? Well, we could have heads, tails, heads, heads, and then tails for the last 5. I guess that would be, right? So what is this really doing is we have 10 slots and we're choosing which 4 to make to be heads and forcing the rest of them, the other 6 to be tails. So for instance, this first one here, right, 4 first heads, that's like reaching in a bag with 10 things and pulling out the numbers 1, 2, 3, and 4. By 10 things, I mean 10 digits 1 to 10. Okay? And then the second one here, that's like saying, okay, I got a bag with the digits 1 through 10, okay, the numbers 1 through 10, and I'm reaching in. When I pull out, I pulled out a 1, a 3. Oh, I missed a head, and there should be one more head right there. I apologize, right? A 1, a 3, a 4, and a 5, right? And that tells me where my heads are. Now, so it turns out, what do we have? What's the size of our event here? E. Remember, E is getting 4 heads when tossing 10 coins. You should write it down. I can't really take the time to write down each time in a video. You should be writing down what the set is. This is really important for keeping it straight in your head. Okay, or the event is, whichever way you want to think about it. It's going to be, what do we say? We got 10 different things, and we're choosing 4 of them. All right? Luckily, each of those is equally likely, right? That's an important thing, and how we counted the sample space and all that business. And so we have 10 choose 4 over 2 to the 10th. So the probability of getting 4 heads when tossing 10 coins is 10 choose 4 over 2 to the 10th. We go, so you can see me plug that in. We got, we want 10 choose 4 divided by 2 to the 10th. And it looks like about 25%. All right. This does, and just to double check, does this make sense? Well, first of all, my probability is between 0 and 1. That's good, right? Second of all, well, it should be fairly high, right? Heads and tails, we would expect, most likely, right? 5 being the highest probability because it's a 50-50 chance. So this 0.25, this makes sense, all right? Reasonable sense. Not, you can't tell exactly, but you know, you'd be very skeptical. I think I'd plug in something wrong if I got something like 0.000002 in this case. Now, suppose I have a bag of 25 marbles, 10 of which are red and the rest are blue. What is the probability of getting 4 red marbles and when randomly choosing 10 marbles from the bag? Okay, so this is actually fairly similar, right? We got that 10, we got that 4 again. But this is an example of a problem that's very similar to the one that we just did, but slightly different. And we're going to see both these types of problems come up quite a bit as we move forward. All right? This first one with the 4 heads, and I'll define all this, this is called binomial. All right? Now, why it is, we'll have to go through that. But look at this other one, 25 marbles, 10 of which are red, the rest are blue. What's the probability of getting 4 red marbles when randomly choosing 10 marbles from the bag? This is just like our senator's problem with the men and the women. Okay, this is called hypergeometric, all right? And it's the same idea. It's the probability of 4 red, which automatically means what? Choosing 10, so 6 blue. Right? Well, first we want to get the size of our sample space. In this case, we ignore the colors, and we have what? 25 marbles, and we're choosing 10. That's all the possible ways of choosing 10 marbles from 25. In our numerator, notice we're not going to have addition because we don't have a different value for the number of red ones. So we're just going to have one thing that's going to use the multiplication. And here's where we picture them in 2 different bags. All the red ones are in one, all the blue ones are in the other bag. And so now my bag of red ones has how many? 10. And how many do I want to choose? 4, right? And then my bag of blue ones has 15. and I need to choose 6 there. Right? Now we'll evaluate this in just a minute, but I want to note is when we're doing these hypergeometric, or sometimes I call them good-bad problems, is we could double check, right? What's going to have to happen if we're doing it like the whole bin is the bottom, the denominator, and the 2 separate bins in the numerator? That means that what? 10 plus 15, that better equal 25. In other words, this number plus this number better equal this number in general, right? Similarly, since I'm choosing out the same amount and just doing it differently, the 4 plus the 6 better equal the 10. Right. Now, hopefully that makes sense. Let me know if you have questions on that. So just again, so we get used to seeing this plugged in, we have 10 choose 4 times 15 choose 6 divided by, and when I have addition, when I have multiplication, I don't need to have that line going all the way. If it makes you feel uncomfortable, you're more than welcome to put parentheses around the top one. 25 choose 10 was the total number of ways out. And okay, so here I end up with 0.32. Right. Good. So that's going to be the end of our slides here on combinations and permutations. And next set, we'll do some more probability stuff with it, and then get more into the differences between these binomial and hypergeometric distributions or probabilities. Okay. Have a good day, and please let me know if you have questions.